Okay, so integrating factor. In this lecture, we're going to focus on solving a linear differential equations of the form dy dx plus p of x times y equal to q of x. And this linear differential equation can be solved using integrating factor method. Okay. So here's the setup. So I'm just want to dive into the procedure because at this point, hopefully you could be able to classify the differential equation, the order of differential equations as a linear or nonlinear differential equations, and with non-constant coefficients, constant coefficients on that, and with homogeneous and non-homogeneous. Okay. So in this setup, the type of differential equation is linear differential equation is written in this form: dy dx plus p of x times y equal to q of x. So q of x has to be different from 0 for the most part, because if it's equal to 0, then you can just use separations of variable to solve for the differential equation. And p of x is usually either a constant different from 0 or a function in term of x. So it depends on the differential equation. The first step is always try to identify what is p of x and what is q of x. Again, when q of x is equal to 0, then you just solve for the differential equation using separations of variable. But in this case, after identifying p of x and q of x, you introduce a new factor, a new term. It's called the integrating factor. It's written as mu of x. And mu of x has the formula of mu of x equal to e to the integral of p of x dx. So you need to evaluate this integral to find the value of mu of x. It's a little complicated, but when you actually do the work, it's not that difficult at all. Now, when you know the value of mu of x, what you do is you multiply both sides of the equation 1. So that's equation 1, which is the linear differential equation that we are working on. So multiply both sides of 1 by the integrating factor mu of x. That is, you have mu of x times dy dx plus mu of x times p of x times y equal to mu of x times q of x. So that's the next step. And I'm going to call this equation 2. Now the next step, step 3, is to rewrite equation as follow. To rewrite equation 2 as follow. So rewrite equation 2 as follows. So you have d dx of mu of x times y equal to mu of x times q of x. So the left-hand side is always going to be this. Okay, let me repeat that. So the left-hand side is always going to be this, right? So derivative of a product between mu of x and y. Why can I get that? It's actually from, if you apply the product rule for the product of mu of x and y, you will get back the left-hand side here in equation 2. Right, when you take the derivative of a product, you have the derivative of dy dx times mu of x, right, plus the derivative of mu of x times y. So this is going to be the derivative of mu of x. So mu of x prime. Okay. So why is that the case though? Let me go back to this integrating factor. When you take the derivative of this, what you're going to get? So mu prime of x give you the derivative of exponential function. It's just exponential function. Then you talk about a chain rule. So derivative of the outside part, the outside function here is exponential function. So that's why derivative of that is still exponential functions. Times the derivative of the inside part or the inside function. The inside function is the integral. So the integral of p of x dx. So derivative, applied derivative on the integral. So that's the fundamental theorem of calculus. Derivative applied on integral. So that's why you get the derivative of the inside function. It's just going to be x, px. So that is the derivative of mu, right? And that's why this is what we have. And from the left-hand side, you have a derivative of a product. So that's why going from step 2 to step 3, even though we start with a complicated expressions on the left-hand side, it's technically just a derivative of a product or the product rule. Now you integrate from here, you integrate both sides of the equation with respect to x. and you're going to get, right, the left-hand side become mu of x times y equal to the integral of mu of x times q of x dx. Right? You integrate both sides of this equation with respect to x, and that's what you got. And to solve for y by itself, you divide both sides of this equations by mu of x, and you get the answer. So y equal to 1 over mu of x times the integral of mu of x times q of x dx. So that's the procedure of integrating factors in solving linear differential equations. So the first step is, of course, the top level step is that you need to be able to identify or classify the differential equation. It's the linear differential equations of this form. You need to be able to identify q of x and p of x. When you know those informations, then you identify and solve the integrating factor of this form, e to the integral of px dx. When you get the integrating factor, multiply both sides of the differential equation by the integrating factor. Manipulate the equation so that you arrive at this equation. The left-hand side, again, is always going to be the product rule or derivative of a product. Then you integrate both sides of this equation with respect to x or with respect to the independent variable, and you get this equation. To solve for y, you divide both sides for mu of x, and you arrive at the answer. Okay. So in this case, in this method, y can be solved explicitly in terms of x or in terms of independent variable. And we're going to apply this particular method to the following examples. So use the integrating factor to find the general solution in particular solution of the initial value problems. So in this case, the differential equation is of the form dy dx plus p of x times y equal to q of x. So p of x in this case is equal to 1. Q of x is equal to x. 1. Then the first step is to evaluate the integrating factor. That is mu of x equal to e to the integral of p of x dx, given that p of x is equal to 1 in this case. So e to the power 1 dx, and you get e to the x. Okay. So even though on the power you have indefinite integral, but in all of the techniques that we're going to learn, this is one of the places that for the indefinite integral that you don't need to care about the plus c. Up to this point, this is the place that you don't need to care about the plus c for the indefinite integral. Okay, I will, if I have a chance, I will explain why that is the case that you don't need to care. Because eventually, if you do add the plus c at the end, everything will cancel out. All the constant will cancel out at the end. So it doesn't matter if you have plus c or not. So you don't have to care about the plus c for this. All right, so the integrating factor is e to the x. Now you multiply the integrating factor to both sides of the differential equations. So multiply mu of x equal to e to the x to both sides of the differential equations. We get e to the x times dy dx plus e to the x times y equal to x times e to the x. Now the left-hand side is going to be the product, the derivative of the product between the integrating factor and the dependent variable always. Right? Then we have that d dx equal to integrating factor times y equal to x times e to the x. Again, why that is the case? So if you if you take derivative of this product, what do you see? Derivative of e to the x is just e to the x, right here, times y. Then e to the x times the derivative of y with respect to x. So the left-hand side, this left-hand side can be written as a product rule. So now you integrate both sides with respect to x, you get e to the x times y equal to the integral of x times e to the x dx. Okay. And you have e to the x times y, you evaluate this integral using integration by parts. Integration by parts. So let u equal to x, so du equal to dx, and dv equal to e to the x dx, or v is equal to e to the x. Again, why did I choose u equal to x and dv equal to e to the x dx? So we talked about this at the beginning of the semester, I mean on Monday, right? About how to solve the integration by parts, that you follow the abbreviations, the ranking of LIAT. So LIATE. So L is logarithmic functions, I is inverse trigonometric function, A is algebraic function, T is trigonometric functions, and E is exponential functions. So X is an algebraic function and e to the X is an exponential function. So therefore you let U equal to the higher rank function, in this case, the algebraic function, or X for that matter. And so you get, from this, you get U times V, that is X times e to the X, minus the integral of V du, so e to the X dx. Then you get e to the X times Y equal to X times e to the X, minus e to the X, plus a constant C. Okay. Now to solve for Y by itself, you divide both sides for e to the X. You get Y equal to X minus 1 plus C times e to the negative X. Or let me be careful here, that is C over e to the X. Or you can write X minus 1 plus C times e to the negative X. Okay. So that's the general solutions, right? In an explicit form. You are also given an initial conditions, that is y of 0 is equal to 2. So y of 0 is equal to 2. So what you do, you find with this information, you can find the exact value of C. So y of 0 equal to 0 minus 1 plus C times e to the 0 equal to 2. Or you have C equal to 2 plus 1, or C is equal to 3. So the particular solution is you have y equal to x minus 1 plus 3 times e to the negative x. Okay, so that's it for example 1. So you can, hopefully you can clearly see the procedure. Always identify if the differential equation you're working with is of the form dy dx plus p of x times y equal to q of x. In this case, p of x is equal to 1 and q of x is equal to x. Right. Then you follow the following steps. So evaluate the integrating factor. Then when you got that, you multiply both sides of the differential equation by the integrating factor. Then rewrite the left-hand side using the product rule. Right? Then integrate both sides with respect to the independent variable, and you get the solutions that way. All right, so let me move on to the second example. In the second example, I have the differential equations of the form dx dt plus x equal to e to the negative t. So be careful with the notation. In this case, the dependent variable is x and the independent variable is t. So p of t is equal to 1 and q of t is equal to e to the negative t. So first thing first, you need to evaluate the integrating factor. So evaluate the integrating factor. So that is e to the, so mu of t is equal to e to the power p of t dt. Well, p of t is equal to 1. Right, so 1 dt, this gives me e to the t. Again, this is the one place that you don't need to care about the plus c for the indefinite integral. Okay. Now the next thing is multiply mu of t equal to e to the t to both sides of the differential equations. We get that e to the t times dx dt plus x times e to the t equal to e to the negative t times e to the t. On the right-hand side, e to the negative t times e to the t, is what you get, right? Is combine them together, the exponent together, you get e to the 0 or equal to 1. Then the left-hand side can be written as the derivative of a product. So d dt of integrating factor, which is e to the t times the dependent variable equal to 1. Now at this step, you integrate both sides of this equation with respect to t. You get e to the t times x equal to the integral of 1 dt, or this is t plus c. Then you divide both sides for e to the t to get x by itself. So x is equal to 1 over e to the t times t plus c. Or I want to write this as t plus c times e to the negative t. Or x is equal to t times e to the negative c plus c, t times e to the negative t plus c times e to the negative t. So these are general solutions. For the general solutions, you have the arbitrary constant c. And to find the exact value of c, you utilize the initial conditions. In this case, the initial condition is given as x of 0 equal to 1. So given x of 0 equal to 1, we get that x of 0 equal to 1 times e to the 1 plus c times e to the negative 1. Sorry. So when t equal to 0, t equal to 0, so 0 times e to the 0 plus c times e to the 0 equal to 1 implies that c is equal to 1. Then the particular solutions is you have x equal to t times e to the negative t plus e to the negative t. Yeah, and that's it for the problem. Let's move on to number 3. It's a very similar procedure. So that is, can you use an integrating factor method to find the general solution and particular solutions of the initial value problem? So in this case, you have a differential equations, but it's not in the form that we usually see for the integrating factor. So you need to manipulate this differential equation a little bit. So that is, you divide both sides for x. So from the given differential equation, you divide both sides for x to get dy dx plus 2 over x times y equal to 10 times x. Okay. Now from here, you can identify that p of x is equal to 2 over x and q of x is equal to 10 times x. So from here, you have p of x equal to 2 over x and q of x is equal to 10 times x. So first, you evaluate the integrating factor. That is mu of x equal to e times the e raised to the power p of x dx. Well, p of x in this case is 2 over x dx. So the antiderivative of 1 over x is ln of absolute value of x. Right? So you have e to the power 2 times ln of absolute value of x. Then you use a logarithm to bring the square, to bring the 2 to the power. So you have e to the ln of absolute value of x squared. Okay, or you have e to the ln of x squared. Okay, or just x squared for that matter, because e and ln cancel out. Now you multiply both sides of the differential equations by the integrating factor. Multiply both sides of the star equations by mu of x equal to x squared. We get that x squared times dy dx plus x squared times 2 over x times y equal to 10 times x cubed. Okay. Now the left-hand side again is going to be the product between the chain rule. Sorry. The left-hand side is going to be a product rule, right? The derivative of a product between the integrating factor and the dependent variable. Then you're going to have d dx of x squared times y equal to 10 times x cubed. Now you integrate both sides of the equation with respect to x. You get x squared times y equal to the integral of 10 x cubed dx. And this is straightforward. So 10 divided by 4 times x to the 4 plus c. 10 divided by 4, you can simplify it, you get 5 over 2. Y equal to 1 over x squared times 5 over 2 x to the 4 plus a constant c. So this is the general solutions. Or you can simplify a little bit further. If you distribute 1 over x squared, you get 1 over 5 over 2 x squared plus c over x squared. So this is the general solution. And to find the particular solutions, you utilize the initial conditions. So given. So the initial condition is here. Y of 1 is equal to 3. So that is x equal to 1, y equal to 3. So given y of 1 equal to 3, you get y of 1 equal to 5 over 2 times 1 square plus c over 1 square equal to 3. And if we do the calculations correctly, c is going to be equal to 3 minus 5 over 2, or 1/2 for that matter. Then you can conclude that the particular solutions is y equal to 5 over 2 x squared plus 1/2 x squared, or 5 over 2 x squared plus 1 over 2 x squared. So that's the particular solutions. Okay. So let me stop right here. That's it for lecture 5.